Hi, I'm Anthony. I'm an associate director at Not So Secure, who, as you've just been told, we're just a part of a Clarinet group. I specialize personally in infrastructure and in cloud infrastructure, pen testing. And as John said, we hack and we teach. So I pretty much do two things, which is I hack infrastructure and cloud infrastructure, and I teach those courses. I have got a bunch of letters. I prefer not to go on about them, but probably the ones relevant for right now are going to be the AWS type ones that I've got. So I am a specialist security certified with AWS, among other things. But personally, I prefer to just go on about the fact that I've been a lifelong geek. I started coding on a BBC Micro when I was about 6 years old. I don't know if anyone remembers those, and I've just been breaking stuff ever since, really. Training wise, I deliver at all sorts of different size venues. So I do the huge trainings at Black Hat and some other conferences. Among those, we do classroom training. I do in-house training, and then I do this weird thing where I talk to a webcam on my own for days straight, which is pretty much the norm for everyone right now. I'm on Twitter, but let's move on from me and talk about why we're actually here. So why is that? Basically, it's become just normal to hear about data breaches where some or all of what was compromised was somewhere in the cloud native for a buzzword. So we're just going to have a look at a quick summary of some of the breaches that we've seen over sort of the last few years since cloud has really sort of seen that huge boost in adoption. And then we'll break down some of the attacks, the scenarios, and what vulnerabilities that in combination actually made those breaches possible and how they happened. To be absolutely clear, I have an hour and I could talk for days, so this is not exhaustive. This is just a small selection of interesting issues that we thought were worth sharing. I'm not in marketing, so I'm just going to do my one shameless plug here, which is the whole set of content that I've used here all came out of our cloud course. So if it does spark your interest, you should absolutely check it out. I love teaching it, so I want you to sign up for it so that I can do more. Cool. So first step then is just to cover a few of the case studies of some recent and recent-ish hacks. So we're going to do this. We're going to do a bit of looking. I've got some pictures in here to try and break up the monotony of my voice and wordy slides. One of the ones that I think stands out to me in terms of impact was a hack of an organization called Codespaces. So I don't know if you've heard of them because they went bust in about 2014 as a direct result of this hack. So what they did was they were a source code hosting provider. They basically provided a space for developers to stick their source code, perform tests on it, make updates and see it going straight into a sort of a test bed environment. And they suffered what they initially thought was a distributed denial of service attack. But what it turned out was that the attackers that were causing these issues for them had actually got hold of some credentials that got them into the company's AWS EC2 control panel. And they were mimicking a DDoS attack in order to try and distract them from the real events. Presumably they were in there trying to steal stuff, whether that's intellectual property or whatever. But as soon as Codespaces realized what was happening, the attackers went into sort of destruct mode and they started deleting things. They deleted EBS snapshots, they deleted the contents of storage buckets, they deleted machine images, EBS instances, other machine instances. Codespaces were sensible enough. They had backups. Theoretically, they could have probably come back from that within hours, if not sooner. But unfortunately, those backups were actually controlled by the same AWS master account, which by this point the hackers were in. And so the hackers just went in and deleted everything. They deleted all the backups, the databases. I don't know if you know, but with cloud accounts, they have a duty to you as their tenant, to securely delete anything that you intentionally remove. So there was just no way that Codespaces could recover from this. They couldn't get any of their data back, and that was it. They had to close their doors for good, pretty much as a result of a single set of credentials being leaked. That is, I would say, probably for most organizations, the worst case imaginable. So we'll now look at a few others. One interesting one was Olin Data. The attackers got hold of the AWS credentials. This time we know that they came directly from a public Git repo where a developer had accidentally released them. And what the attackers did was they spawned 20 of the largest instances possible in each of the AWS regions worldwide. I'm not sure exactly how many there were at the time. There are currently 22 regions, so you're looking at 20 times 22 instances at the highest possible billing rating on AWS. And they were just using those to go Bitcoin mining, basically. So the average cost at the absolute peak of this was $20,000 a day. They caught it around about the 90,000 mark, because as you can see from this little chart here, their previous spend was nothing. So it was fairly clear fairly quickly that something was amiss. Now you can imagine if you were a larger organization that had a large spend anyway, and maybe if they caught you at the peak of a sort of a large elastic increase in spend, it could potentially be quite some time before you realized, if you realize at all, that this was not normal usage and that something shady was going on. So huge potential cost. Company you may have heard of, Tesla. They got their administrative credentials accessed via a Kubernetes console. Having gained the credentials, they used those to access the dashboard, and they launched similar things, some crypto mining scripts. They actually reduced the CPU usage demanded by those scripts in order to mask their behavior so that it was not obvious. So if you looked at your dashboard, you'd see sort of CPU spikes and think there's something wrong here. But by reducing that usage, they flattened the curve a little bit. They also masked their IP addresses behind some services such as AWS CloudTrail, which are technically there to help you defend your environment. And they were able to abuse those in order to actually hide their tracks and make it less obvious what was happening. In addition to this, they also pulled out some business data from some S3 buckets. Fortunately for Tesla, none of that was sort of publicly identified information for any of their customers. So it was just vehicle servicing data and relatively unsensitive stuff like that. We'll go a bit more meta at this point, so we can't necessarily expose who these ones happen to, but exploitation of SSRF, or server-side request forgery, which I will go into a lot more detail a bit later, so bear with me on that. They were able to exploit this to obtain access to what we call the metadata service, which is effectively a value store that cloud providers have, which includes a whole bunch of internal data. And included that would be service tokens for accounts, so that they could effectively, they're like temporary security credentials. And they used those to enumerate the S3 buckets associated with the account, and they found one that contained the key files that were used to access all of their EC2 instances. They were also able to enumerate those instances. They found some instances with high power roles. They gained access to those using the key files that they'd recovered from the S3 buckets, and they're able to backdoor the entire AWS account by adding IAM star capabilities, which effectively means they had complete control over the entire user space within the account. As I say, we can't give you the exact, but there is a very similar write-up on ThreatStack, which you can take a quick look at. A similar sort of starting point, we have another one that started with SSRF getting access to metadata, which I'll go into a bit more detail later, but it's a very common and quite interesting entry point. This time they couldn't directly read out the S3 buckets, but with the account ID and region, it's actually relatively trivial to perform a dictionary attack and discover buckets that way. Having done so, they gained access to one of those S3 buckets and found that the credentials did give them right access to it. And on that bucket, they found source code for an application. So they planted a backdoor inside the source code, and then they couldn't even have known immediately, but they had a bit of luck where CI/CD software was in place, which effectively took that code anytime any changes were made and automatically deployed it to the company's official website. So the next thing, they had a shell, they had a full backdoor on the official website. Another one where we can't give you the full details, but an AWS account credentials were leaked. We can't say exactly where from, but the attacker went in, they gained access to backups of all of the production databases. They got SSL certificates, including for the company's corporate website. They got the source code, Confluence, Jira, S3 buckets, everything. So they had everything they needed to effectively imitate the company, set up a rogue website. They had all of the data. They basically had everything. And the final one that I'm going to talk about now is, fortunately, this was discovered by a security researcher. So there is a full write-up on HackerOne, which is a bug bounty site. And the researcher reported this via HackerOne to the organization, to Shopify, and it was resolved. As far as we know, it was never exploited by anyone maliciously. But but when I get to the end, you'll see why that would have been really, really bad. So what the researchers did was they went in, they created a store. So they've effectively signed up for the service on Shopify, generated a store, and they were able to modify the template of the password.liquid that is a part of that, which you would expect to have access to as the owner of the store. And they were able to insert a script into that which accessed Google Metadata API. With that, they couldn't actually retrieve the information. They only had a script that accessed it. So the next thing they did was they installed the Exchange app, and part of that process generates a screenshot of your store to use as the listing icon, effectively. What they did was they were able to use the script that they'd inserted in the password.liquid to add the output from the metadata API as JSON alt text for the image of the screenshot, which meant they were then able to review that by just hovering over the image. They were able to see the alt text. And using this, they dumped out kubeenv, which allows them to get hold of the kubelet certificate and private key for the entire host. Basically then meant they were able to run arbitrary commands as root across every other container on that host, which is effectively other people's Shopify stores at this point. So they were in control of an entire host of Shopify stores. So very, very serious. And as I say, fortunately, this one was exposed by a researcher and not a malicious attacker. So that is a fair number of different approaches and different very, very serious outcomes. So let's do a little bit of this, a little bit of coding. We're not actually going to stick skulls in people's code, but I liked the graphic. So before we get too deep into individual breaches, individual vulnerabilities, we're just going to run through quickly what we call our art of hacking methodology, which is just a very, very simplified version of the steps that an attacker, again, whether that's a legitimate pen tester or a malicious attacker, might go through. So step one, we're always going to be in a position where we don't have all the information we could have. Again, as a malicious attacker, you probably have very little. You might know the name of the organization you're attacking. You might be targeting someone specifically, but a lot of the time you're just an opportunistic attacker who's found a vulnerability floating somewhere. As a pen tester, you often don't have a lot more than that. You may have been given a brief and a list of IPs, but a lot of the time you don't have a great deal of information. So step one is to spend a lot of time researching and enumerating and information gathering the target in general. And that's both from a hardware perspective, trying to find vulnerable services, vulnerable systems, as well as from a sort of a soft or wetware perspective, trying to find people and information which may well gain you your initial foothold. And then we go through the process of identifying vulnerabilities in those various resources that we've discovered. And a lot of the time, the vulnerability will be a person. The vulnerability will often be someone that we will phish. But we identify the vulnerabilities and we prioritize them, and then we start working through attempting to exploit them. And as I say, a lot of the time that will involve phishing, that will involve hitting external services. We might get lucky and find an outdated or otherwise vulnerable misconfigured service. We might have to phish, we might have to go through several steps of social engineering. It varies case by case. But pretty much once we've got that initial foothold, that very first step inside their perimeter, everything from that point onwards is what we call post-exploitation. So that's the process of finding additional privileges, exploring internally, trying to pivot between services, between systems, trying to gain access to further resources inside the network. And from that point onwards, we're going to use all the privileges that we can find, and we're going to go back to step one, and we're going to go through enumeration information gathering again, because the chances are we now know a lot more than we knew before. We now have access to a lot more than we had before. And so we're going to start from the start again, and then we're going to repeat that cycle over and over again. And it will probably take 3, 4, 5 iterations of that cycle, if not more, before we've reached the end of the test and found everything there is to find. So as I mentioned, I've only got limited time. I'm already, 20 minutes in, so I can only cover a certain amount. But just to give you an idea of what we would cover on the full 2-day cloud course, for example, we've got a day and a bit on attacking cloud services, and then we've got the rest of day 2 is spent on defending. I'm going to go very, very little into defending, I'm afraid. So hopefully you weren't expecting too much on that front. What I'm going to demonstrate is a bit of the enumeration process. We're going to cover a few areas of attack surface. We're going to look at how you might gain entry. We'll talk about a couple of types of attacks, for example, the financial impacts. We'll cover a bit about Google dorking, which is a bizarre term. We'll talk about post-exploitation and very, very briefly about backdooring and maintaining access. And that's pretty much all I've got time to fit into this. And again, it really is sort of, we've picked out one, maybe two instances from a great deal of content on each of these subjects, just to try and give you a taster, really. So I'm going to start with enumeration, as you might expect. And first thing to understand is that there are a huge number of cloud services, an absolutely massive number. I don't know if you've ever been into the AWS dashboard and just tried to look at the service list, and it's just so long. So we try and break these down into a few different categories. So you've got software as a service, things like the sort of online cloud storage providers like Drive and Dropbox, things like the Salesforce Online CRM, Office 365 is just a massive suite of online software as a service applications. Databases often fit into this category. You've then got function as a service, which is where you actually deploy code directly to a container. You've got no control over the container, you just write some code, and is often referred to as serverless, which is a term that really offends me because there's obviously a server, but it's referred to as serverless because we don't interact with a server. We just write some code and deploy it into a cloud, and it really does feel like a cloud. It just sort of happens. So you're only really responsible for the code. Then you've got platform as a service, which is where you get to deploy some software to a platform, but without really having to worry about the OS underneath. And then finally, you've got infrastructure as a service, which is the closest in behavior to having a VM, to having a machine on site. You've got much more control, but you're also there, therefore taking on a lot more responsibility. You've got to control the OS, you've got to keep it up to date, you've got to harden it, and so on and so on. So in terms of trying to find these services, there are a few things you might try. One of them is Google dorking, this bizarre term I referred to earlier. It's sometimes called Google hacking as well. It's not really hacking because it is using the tools that are available to us pretty much exactly as they're intended. The fact that it's for a malicious purpose, it doesn't necessarily mean we're misusing them. So we've got the advantage that cloud services tend to use a very predefined set of subdomains and the way they're organized, which means that we can quite quickly try and identify resources by searching specifically within those predefined structures. So for example, .s3.amazonaws.com, we know that that's where S3 buckets are going to be. Similarly, star.azureapi.net and so on. So in a cloud platform, we could identify potentially misconfigured cloud services by using Google Dorks, such as the site controller here. So we can say we are looking only within star.s3.amazonaws.com, and we're looking specifically for the domain of the organization we're attacking. You could be looking for a static website, in which case you can be even more specific. And you could use those looking for, passwords or whatever. One of the other things we might do is review the DNS records related to the domain. So the domain is probably one of the things that we know very, very early on about the organization we're attacking, and we know what domain or domains they operate with. So we can look at those name records, and we can find, for example, MX records. They will let us know who they use for their emails, whether they've got any filtering type solutions in place. We can look at NS records to find out where they're registered with, whether they have any DNS protections in place. We can look at text records, which let us know whether they've completed any domain validations. So for example, when you take out a lot of online services, SaaS services in particular, you often have to verify the domain that you're integrating. And you do that by inserting a text record into your DNS settings, and that text record can be checked publicly, and then the provider will be able to validate that you definitely own the domain because you were able to insert those records. Now for us, that means we can retrieve all of those text records and see who you have validated with, and we can take that information away and look at services that you are interacting with and whether we can intercept any of those. So I'll just really quickly show a video of that process. Hopefully is going to be quite easy to pause in the right positions. So the first thing I did was a very, very basic NS search. So I'm using a tool called dig. Victim.cloud in this instance, that's the organization we're attacking. So that's, you can imagine victim is the organization name and .cloud is going to be your .com or whatever. So we're looking for NS records, and we can see that they've registered with registrarservers.com. I then do the same thing for MX records, and you can see that they're using registrarservers.com, but you might see Gmail here, you might see Outlook here, and you might also see things like Spam Assassin or Mimecast or whatever as well, if they're using additional services. And then the final one here is I've done an any, because I just want to see everything. And I'm using Google's DNS to check this, and I can see that I've got a start of authority, I've got name servers, I've got A records, which are some endpoints that I'd certainly go and investigate, which may or may not be cloud-based. And then I've also got these text records down here. And that lets me know that they have validated for SPF, so that's part of emails with registrarservers.com. I know that they've done Facebook domain verification, Google site verification, so they might be using Facebook and Google as sort of authentication platforms. And they've also registered with Have I Been Pwned, which is obviously very sensible of them to find out whether any accounts related to their host have ever been compromised. So I've mentioned that domain is one of the things that we definitely know, and we've looked at the records associated with that domain, but something we've missed at this point is looking for subdomains of those domains. And so something that organizations very often do is they register subdomains to relate to different services and different parts and different activities. So for example, I might have helpdesk.myorganization.com for accessing the help desk. I might have blog.myorganization.com, that sort of thing. So if I just do a sort of a dictionary set of queries against common subdomains, I may well find some interesting things. Another area to look is I might be able to find registered SSL TLS certificates, which may tell me about additional subdomains. And something that's also very common is to use subdomains to link up SaaS provider URLs to your primary domain. So for example, if the SaaSprovider.com registering with them, they might provide me a subdomain of their domain, which would be organization.saasprovider.com. And I might quite like to use my own domain. So I might set up saasprovider.organization.com and have that pointing to, using a CNAME, the organization.saasprovider.com portal that I've been provided with. Now, that certainly will help me to find some of those SaaS providers. But another interesting issue there is called subdomain takeover, which is where this CNAME here has been set up, but the other side of it, the target of it effectively, is available to register. So that might be because it's expired or was never registered or whatever. That means anyone could come along and register with that SaaS provider and gain control over this subdomain of the SaaS provider legitimately. Having gained control of it, they have a CNAME from my host, my domain, pointing to this subdomain that they've got control over, which effectively allows them to demonstrate, to prove ownership of that. Even though they don't actually own it, I've given them an ability by making this misconfiguration to allow them to demonstrate ownership. So that's quite a dangerous scenario in itself. And we'll just quickly show you the process of finding some of these. So the first thing I've done is I've gone to census.io and I'm using this as a service just to look up certificates. And I'm going to type in victim.cloud up here, and you can see that we've got the victim.cloud primary domain certificates, which run with Let's Encrypt. But down here, an Amazon certificate has been registered for AWS lambda.victim.cloud. And so we now know that there is definitely a portal operating here that's been registered, and it certainly looks like it probably points to a service running within AWS, although names can be deceiving. The next thing I'm going to do is I'm going to use a tool called DNSCAN, and I am going to give it a domain victim.cloud and use a word list, which I've just used a basic subdomains.txt. It's just a list of common domains. It quickly runs through some of the steps we already did, but the interesting part is what comes up here. And you can see these are the words it's running through, and it's from that word list, and it's found a whole bunch. It's found the main domain, it's found AWS lambda.victim.cloud, it's found DB, web app 1, web app 2, and www. So those are now all endpoints that we can potentially go and investigate, and some or all of them may well be hosted in the cloud. Spoiler alert, they are all hosted in the cloud because they're part of our cloud course. Okay, so SaaS providers we talked about briefly. Let's go into just a little bit more detail. Much like we are able to look at subdomains of our domain and potentially find the subdomains of SaaS provider domains that have been provided to us, these sort of portals, we can do the same thing the other way around. We can look at all of the common SaaS providers, all of the well-known SaaS providers, and look for something, sort of a common pattern of the organization's name as subdomains, and to find if anything's registered. Not necessarily all linked, so there is a chance that we're not going to find things one direction and we will find them the other way. Equally, not all SaaS providers actually give you dedicated subdomains, so you might be able to find things from the other end and not from this end. So it's just sort of a filling in the blanks exercise, really. The thing to remember here is that this is not necessarily 100% accurate because anyone can register any name with these SaaS providers. So just because you find something doesn't necessarily mean it belongs to the organization. So certainly on a sort of an open pen test, this would be a case of go back to your contact within the organization and verify that these are accurate findings. One of the only other thing that I can think of off the top of my head that we haven't looked for at this point is storage containers. So certainly S3, Amazon S3 got quite a bad name a few years back because an awful lot of S3 buckets were being found exposed, publicly readable, with sensitive information in them. So this is probably the most infamous of all of the cloud issues. So the biggest concern we have is exactly that, storage buckets being set up, storage containers being set up with improper permissions. Generally speaking, that's world readable. Although very occasionally you might find you have write access as well, which is even worse. And so our concerns here are going to be data leakage. If we find one of these, we could potentially just exfiltrate any kind of data from them. If we can list and even write objects, we may well be able to fetch or write to content to folders. And in the most severe case, as one of the case studies we covered, you may well find that that source code you can write to and it ends up being deployed to our website. So generally we find these just by guessing. We find these by brute forcing, dictionary attacking, random URL formats. This gets particularly interesting in cases where a URL shortener is in use, but we're going to keep it simple and use a tool called S3 Cruise, which sadly I think is no longer maintained, but there are plenty of tools out there for doing the same thing. And what I've done initially is I'm doing this unauthenticated. So what S3 Cruise does is it uses your AWS command line configuration to perform these searches. So what I've done is I've deconfigured my AWS command line so it hasn't got a username at all. And you can see that even unauthenticated, it can find the matches. So we've just given it the name victim, that's the name of the organization, and then we've used a list, dictionary list of potential bucket names, and it's found one called victim auth, it's found one called victim private, and it's found one called victim public. You can probably guess their configurations from that. That is intentionally obvious. But what it's done is it's attempted to perform a directory listing on each of them, and it said it can't because it doesn't have credentials. So what I'm going to do is I'm going to run AWS configure, and I'm going to blank out the credentials because these are mine. I'm not going to share those with you. I'm going to run the exact same search again, but this time authenticated, and you can see that it's got slightly different results this time. I let it go too far. It found victim auth, and because I'm now authenticated, what authenticated access effectively means is only users who are authenticated to an AWS account can read the file, can read the bucket. Now, anyone can register an AWS account. So effectively, this is no different to making it publicly available. And this is sort of the new S3 issue, really, the new public, because people are assuming that putting it behind authentication means it's safe, but it doesn't, because anyone can go and authenticate. So I'm authenticated to an account that has nothing to do with this actual S3 bucket, and yet I'm able to do a directory listing, and I will be able to retrieve that file. Victim private is actually registered as private, and so I can't do anything. I get an access denied error. And then finally, victim public, as you might expect, I can read the inside of it and I can access those files. And I'll just show you the exact same thing using the browser. So again, this is unauthenticated. I've just gone to victimpublic.s3.amazonaws.com. That's the standard endpoint. And I can see there's a git repo.zip file and a public file.md file. And I'm going to retrieve that by sticking it up here. And that's the file I was able to download and access. And I can do the exact same thing for victim auth. You can see within the browser, I get access denied because my browser is unauthenticated. However, if I use the Amazon command line tool, I can run an ls of victim auth and I can see the file, and I can actually do a copy with a cp command, and I can now cat out that file I've downloaded and stored it locally. So any authenticated user, whether they're related to the account in question or not, can access auth only buckets. The rest of this video is doing this exact same thing, but using a tool called GCP Bucket Brute to do the same thing on Google. So I'm going to skip ahead because we're very limited on time, but the process is more or less identical, and Google and Azure have the exact same issues with public, auth, and private, and the confusion surrounding those. So having found a number of issues, we found a number of endpoints, we found some exposed buckets, we found a lot of stuff already in a very, very short time. We're going to look at how we might try and gain that initial foothold. So I mentioned before how we have these different categories. We've got infrastructure as a service, container as a service, platform as a service, function as a service, and software as a service. And you can see that as you move right on this diagram, what you do effectively is you offload some of the responsibility onto the cloud service provider. So with on-premise, you are obviously responsible for everything. You're responsible for that physical security of the building that the servers are stored in. You're responsible for the security of the servers themselves, for the networking, for the network level load balancing. You're responsible for everything. You offload a lot of that because we obviously aren't in control of. We'll pick on Amazon here. We're not in control of their data centers. So we offload all of this immediately by taking on something like infrastructure as a service. We are, however, responsible for configuring and maintaining the OS and everything above. By moving a step further to the right into a container as a service, we've managed to offload the OS and the middleware. And we can assume, if we're using one of the big three at least, or one of the larger providers, we can assume that they're going to do a good job of ensuring that these are secured to the sort of current accepted best practices. So we can probably rely on a reasonable level of assumption that if there is a compromise, it's not going to be any of these green boxes that have caused it. We are still responsible for runtime and upwards. And again, by moving further to the right, we offload more and more and more of that responsibility. So in terms of security, it makes sense really to only take responsibility for what you absolutely need to. Now, we talked about Google Dorking earlier, so let's just give it one quick more revisit. We're going to use that same cite command that we talked about earlier. And we're going to look within, in this case, S3 within the EU West 1 region on AmazonAWS.com. And I'm going to look for files of type text. So any text file that's stored within an S3 bucket and also contains the term pass. And that on its own, you will be amazed how many responses you get for potential text files containing plain text passwords that people have just saved to S3 buckets and left public. You can, of course, take this steps further and go more and more complex, make more and more effort. But it's not just Google Dorking that we can do. We can also look on GitHub. So, for example, you could look within GitHub code for code that mentions the organization we're attacking and that contains a term like API key or secret key or AWS key, that sort of thing. Showdown, if you're familiar with it, is effectively Google for hardware. So again, we can look on there for any sort of exposed services, potential entry points. And finally, archive.org. As we know, nothing on the internet is ever truly deleted. We often find that developers accidentally expose secret keys, passwords, that sort of thing, and then do the sensible thing and delete it. But unfortunately, because nothing's ever deleted, you may well find on archive.org or similar copies of that information that are still present and still exist. So this is just a quick example. We searched GitHub code for default endpoints protocol. And at the time, so this was, I think, around June, July last year that we ran this search, we had 67,000 responses. And of the top three that were on the screen, this one, they've been redacted, they've been removed. But the following two both had active account keys stored in code in GitHub repositories. Now, if we make some huge assumptions here and extrapolate from that, you're looking at possibly 40,000 exposed keys if that ratio holds. Pretty serious. Now, I am aware that GitHub, I think they're still in beta of this, but it's a service that actually reviews commits as they're being made, looking for certain types of account key and API key formats, and actually notifies the organization that a key has been committed, and those organizations can actually go in and then automatically invalidate those keys. So I know that Slack are doing this, and I assume, given that GitHub's owned by Microsoft, they may well be doing this with Azure. Whether or not they're playing nice with AWS, that's another question, and I have no idea. But hopefully we'll see a reduction in this kind of thing happening going forward. But for now, it's certainly very much alive and kicking in certain areas at least. Now, looking at services themselves, excessively exposed services of any kind are going to increase your attack surface. Misconfiguring those services could easily lead to someone gaining access to unauthorized access to data, to the system underneath. Who knows what they could gain access to. And this is something that we see far too often. So what this is a screenshot of a AWS security group's configuration page. and the security group that's been configured, they've called it test, and what they've done effectively is they've opened up all ports in all protocols to all sources. Basically, it's like turning your firewall off. It's like bypassing your firewall completely. You would never do it inside your corporate network, or at least I certainly hope you wouldn't. And yet, for some reason, because of this sort of perceived isolation, I think, of cloud services, this is an issue that we see very, very frequently. Exposing these services means anyone could go in and access them, and as I say, any kind of misconfiguration could lead to your entire host being compromised. Now, one of the number one targets for us when we find out a set of services we're attacking are hosted in the cloud is what we call the metadata API layer. Effectively, it's a layer provided by all of the cloud providers. They've all agreed on a very similar format for this as well, which basically shares system environment information. So you might recall this is what we were accessing through SSRF in the case studies, a couple of the case studies from right at the start. So generally speaking, you just make HTTP requests to a non-routable IP address, which is 169.254.169.254. I don't know how they all came to agree on that, but it's usually non-routable for network cards that don't get configured to a network correctly. Some of the providers require extra headers, so this prevents potentially reflected attacks because you can't reflect a header as part of an SSRF type attack. So by requiring that header, Azure certainly are very well protected from this. AWS and GCP, yes and no. I haven't really got time to explain that in great detail, but sometimes yes, sometimes no. AWS has an additional thing where they don't actually allow access to the metadata API from functions as a service. So Lambda functions can't access the metadata API. However, there are ways around that as well, because that information does still need to be exposed to the function. It's actually done in environment variables. So if we gain access, we can retrieve temporary creds, their service account credentials. So it's effectively a full set of security credentials to allow us to configure our command line tools to access the entire AWS APIs. They're temporary, but they last for minutes to hours. And so generally, if we find that we've got access to that, that's going to be our number one target for gaining access and then hopefully pivoting between services. Now, SSRF, I've mentioned it a few times now, so I should probably explain what it is. Basically, it's a vulnerability that allows an attacker to trick the application into sending requests for them and reflecting the results back. The situation where this is useful is if we have compromised a host that can see things that we can't. So whether that's a host that's on the edge of a network and it can see inside the network, we can't get inside the network, but we can ask it to send requests to internal systems and to return the results back to us, which means we can use it for all sorts of things, potentially accessing web pages, internal applications, but also weird stuff like performing port scans and acting as a proxy. Now, a really good example of a HTTP request that we wouldn't be able to send externally, but that we can from internally, is access to that metadata API, which means if we're able to have reflected requests sent onto that API and the results returned to us, that is a really good way of gaining access to those service tokens that we were talking about, as temporary service account tokens. So I'm going to do a couple of demos. This is a longer one here. The first one here is going to be our web app 1.victim.cloud that we discovered right at the start in the enumeration phase. And you can see that what it effectively is a proxy. It's a bypass application that was produced at some point. It's now unsupported, but it's still running, which hackers find very, very exciting when they find things are no longer supported, but still present. And what we've done is we've just gone to a not so secure website, but what's actually happening is we're still at web app 1.victim.cloud. We've got a parameter URL equals, and URL equals notsosecure.com, and then it goes to the site, it accesses it, and it shows us what it sees. Sounds useful. Let's ask it what my IP address is. And it's found an IP address. So what this does, it goes off to a service called what'smyip.org, and the service responds, this is your IP address. So effectively, this is the IP address of the device that accessed what'smyip.org. Now, if I do the same thing locally, I have an entirely different IP address. So I can say with some confidence that I didn't send that first request. It came from the host that I was compromising. Now, if I look up that IP address, I can see that it's owned by Google. So I am probably compromising a host that's operating under Google Cloud. Now, if I send that to metadata.google.internal, which is effectively Google's name server for for 169.254.169.254, let's rewind that a little bit, I get some responses which are endpoints that I can explore within that metadata service. So I'll do the same thing using curl requests locally. So I'm doing the exact same request here, and I've received, in the first case, compute metadata in 0.1. So I'm going to add compute metadata to the end of my request, and I now have v1 and v1 beta 1. Now v1 requires the headers that I was talking about. It requires metadata version Google or something like that. So I'm not going to get a response, and you can see here I've had no response if I do it in a browser either. But if I change that to v1 beta 1, the header requirement is not present. Now this was supposed to be deprecated in December, but it hasn't been. So I'm now going through the service through the endpoints. I found one called service accounts. I'm going to look inside a service account called Terraform Robot Storage, and I found one called token. And if I look inside that, that is a temporary service token, and that's how easy that was to retrieve. Now, if I do a very similar thing, just show you in the browser as well. Here's another one. This one's hosted in GCP functions. So instead of being a web app hosted within GCP, this one's hosted in functions. We do the exact same thing. There's another IP address that's not mine. And by asking it to proxy 169.254, I found compute metadata, and I'll follow the exact same steps, go through v1 beta 1. Just stick that at the end, and I'm just going to fast forward to the end, and again we pulled out an access token just as easily, so we can do that both from a web app and from functions. And now very quickly we're going to skip across to another one. This one's hosted on AWS Lambda. As I mentioned, AWS Lambda doesn't have access to the metadata API, so this one isn't rendering the page, but if we look inside, we've done what's my IP.org, and there is another IP address. Not quite so easy to see it in all that code, but it's there. And what I've attempted to do is access the metadata API, and I've received a error connection refused because it doesn't have that access. However, fortunately, if I take this a step further, we've got something called directory traversal or path traversal, which basically means we can access files and directories outside the web root folder. So we manipulate some variables, and we can potentially reference files on the file system of the host. Whether that's absolute file paths or using .. slashes to basically go up one directory and effectively browse the file system. And if we manage to exploit this, we can read and execute files on the victim host. Now, one of those files on a Linux file system is your environment variables. So this is where we were a minute ago. I'm now going to say, show me file etc password. And it's going to show me the contents of the user list file for that host. Now, if I do the same thing, but instead I look for file proc self environ, just as part of the curl request, you can see down here we've received a bunch of environment variables back, and we'll just quickly highlight. We have got an AWS secret access key, we have got an AWS access key ID, and we've got AWS session token, and that is everything we need to gain access using the Amazon command line tool. That is a full set of security credentials. The final one I'm going to show you is remote code execution, which is the most complete exploit, really. We can now run code on a system. So generally speaking, this occurs because of improper user input validation. Having gained access, we can run code, we can run commands, we can steal data, we can do pretty much anything. So it's a slightly different application. This one's Web App 2. I'll give away that it's hosted on Azure, this one. And you can see that each of these diagnostics tools that seem to be here, what they're doing is they're changing what's in the URL up here. And it looks like it's effectively a bit like a web shell. So you would kind of hope that this sort of diagnostic page wouldn't be exposed to general users, but it happens frequently enough. And so what we're going to try and do is we're going to overwrite that. And if I run uname A, sure enough, my command gets run. So I'm going to do a quick command. This weird dig command here reveals the IP. And again, it's not my IP, so I'm definitely able to get it to go off and access things. Now, because I've got full code execution, that means, you can see this one's owned by Microsoft, so that's Azure. That means I'm actually in a position to send full curl requests with headers, which means I can send the header for Azure, it's metadata true, which means I'm able to send the full metadata request, including the header, and get a proper response. So we're going to send that, and certainly we are inside. I'm going to do the same thing with curl requests. We're now sort of in curlception because we were sending a curl request to webapp2.victim.cloud, and the command is to send a curl request with a header through to the metadata API. The formatting for Azure's is slightly different, but that doesn't matter too much. That's what's happening. And if we just keep on adding the endpoints, we can browse through that. And again, you could pull out some tokens and various other things. So we've got a foothold. Let's talk about post-exploitation then. I'm slightly worried I'm going to go over on time here, so I apologize now. So what we want to achieve here is we want to enumerate again, and we want to pivot. So enumeration is the key. We need to figure out what the token or tokens we have access to. And then we want to try and pivot between the services they can access, find more, compromise further, find more tokens, get more privileged accounts, and eventually gain control to everything we want to gain control of. Generally speaking, passwords aren't going to help us. Generally speaking, they're going to be increased complexity. And so unless we can clear text retrieve passwords, we may as well forget password attacks. And let's never forget that we don't need super admin necessarily to get what companies are afraid of us getting. So yes, super admin would definitely mean a full account compromise, but we can probably get your data without going that far. Now, in the interest of this, we've released a tool. So you can get it from our GitHub account called Cloud Service Enum, which includes an AWS, an Azure, and a GCP version for effectively taking an exposed token as temporary service credential and using it to find out what exactly it has access to. And so I'm going to really quickly demo. This is actually a slightly older beta version in this video, but of the AWS version. So these are the credentials we pulled out of Lambda earlier. Just going to very quickly reformat them, pull out the parts that are important. And this is going to be the command we're going to run. So we need to feed it an access key, a secret key, a region, and a session token. So that's those pulled out of the metadata API. We'll put them in. You can see the region matches up, and then the session token. And now when I run that, it goes off and it just runs a whole load of API queries. And you can see that immediately it's pulled out those bucket names that we found earlier. It finds some stuff in EC2. It finds some additional stuff. I think it finds some snapshots. I'm going to skip this, move ahead, but effectively it just runs every conceivable check to see what this token can do. And then we can repeat that for as many tokens as you want. One of the things that it found was snapshots. Now, a snapshot basically is just a point in time backup of an instance. So you backed up your instance, you save the snapshot inside your account, that's the end of that. But if we gain access, if we find a way of making those snapshots public, possibly because of exposed credentials or whatever, we can actually clone those out of your account into our own user account, our attacker account effectively. We can then launch an instance inside our account under our ownership, and we can mount that storage. And having done that, we are effectively the owner of that. We are now the super admin. And that means we can pull out stuff like your SAM database from Windows, which would normally be protected. We can look inside your etc shadow file because we are root. We can look at config files for your various apps. We can look at everything that would normally be very, very well protected. It's now ours to do what we want with because we own the snapshot. And all we needed was the ability to clone it out of your account. Now, having done all of this and potentially gained some accounts, gained some privileges, the next step is going to be to try and establish some persistence inside your accounts, inside your environment. So there are a few steps we can take. We can use the Amazon command line interface, for example, to extend or generate tokens we have. We can set the expiry time ourselves. So these are usually meant to be temporary keys, but we can make them as long as we want within reason. So suddenly we've got these sort of apparently temporary keys, which are sort of going to fly under the radar, but we can make them last a really long time, giving us persistent access. You could create new users if you've got IAM access to do so. That said, I would argue that's one of the noisiest things you can do inside someone's account. I'd like to think I'd notice if you started adding users to my IAM roles. So probably more likely would be to add access keys to existing users. So effectively you're gaining control over a number of existing users by adding access keys to them. And those are a lot less obvious until it comes to audit time, assuming audits are even being done. One of my favorite tricks, you can set up a Lambda function, which triggers every time a new user is created and sends out an access key to your backdoor. You've effectively now got control over every new account that gets added to the environment. Now, if I was an auditor and I saw account got added and I checked that it was a legitimate account add and I said, this is all good, everything's fine. And then I saw a new access key being added and created to that account immediately, I would say, that looks fair enough. I will just assume that that is an intended action. It's a logical process to follow. Create a user, add an access key, and I wouldn't even question it. But that access key in this case is actually going out to the malicious user that created the backdoor. You can also create new roles and attach those to existing roles so that You're not having to create users or add roles to users. You just add roles onto other roles, and again, flying under the radar. And again, you can set up a Lambda function to actually add, anytime a new role is created, it adds it to your existing backdoors. And then finally, the icing on the cake here, you can actually use a thing called the update assume role policy trigger to notice when if your backdoors ever get discovered and deleted, and to automatically replace them. And because it's got about a 5-minute to 15-minute delay on it, they will get recreated, and the person that noticed them and deleted your backdoors probably won't even notice they've been recreated automatically. So it's sort of the ultimate troll in that sense. So let's say tattered and torn, the red team have kind of won here at this point. They've got control over everything. Impact-wise, you've got all the normal impacts, so all the usual concerns, things like theft of intellectual property, leakage of sensitive data, reputational damage, DOS, sabotage, that sort of stuff. That's the same whether they've attacked you in the cloud or attacked you on-premise. But the thing about cloud is it introduces some additional concerns. So any kind of cloud account, role, or policy misconfiguration could lead to a really significant financial impact. Worst case, as we talked about earlier, but an attacker with permissions can also spawn instances. So for example, these tens of thousands of dollars a day costs, like we saw in the cryptocurrency mining. They can also do some really sly things if they really are just trying to hurt you. So there's a role called Secrets Manager Read Write, and there's a tool called AWS Secrets Manager, which is effectively a value store where you might put credentials. Now, if someone finds they have access to a Secrets Manager Read Write role, which is the only default rule for accessing the Secrets Manager, they could write records into your Secrets Manager, and AWS charges you 40 cents per month. So if I start sticking hundreds of thousands of records in your Secrets Manager, I don't really gain anything, but I can cost you a lot of money very quickly. But as I say, worst case, remember the studies from the start. Even a single set of leaked credentials could lead to your entire company going bust overnight in the absolute worst case. I'd like to think most people are possibly not in quite such a vulnerable position. So you're probably thinking at this point, if that's only the tip of the iceberg, then I've got some serious work to do. There are obviously some steps to defend, and I don't have time, I apologize, to stand behind this bloke and tell you what he's doing. But you could protect the metadata API to some extent. You should monitor, you should log, and you should have alerts set up. There are vendor native tools for doing this. There are third-party tools, there are open source tools. You can even go so far as automatic remediation. We do a really good example on the course of correcting something as soon as it's detected that a change has been made. If you're using infrastructure as a service, then host security comes inside your area as well. So you've got to go do all the standard stuff that you would have done anyway. If you were using on-premise. There are some really good tools out there and some really good benchmarks for auditing and benchmarking. So CIS is a really good example of, they've got a set of benchmarks for Amazon, they've got a set of benchmarks for Azure, they've got a set for Google Cloud Compute. Audit your environment, audit images as well, all your machine images, Docker images, container images, everything. And it is a continuous process. So much like we will always have said to you, when you do a pen test, that doesn't mean that's it. You do another pen test, however many months later is appropriate for your business. Auditing and benchmarking and monitoring and managing your cloud environment has to go on continuously, because this stuff changes constantly. The whole point of cloud is that you can move in a very, very agile manner. Now, agility has one major outcome, which is that stuff changes and stuff changes quick. And you need to stay on top if you want to keep yourself safe. Thank you very much.